So similar to capacitors, we can connect resistors in series. And we can connect them in parallel. Now, one side little technical note. When we talk about batteries, delta V is the actual potential difference you get from your battery, which may or may not be the full 9 volts if it's a 9-volt battery. In an ideal battery, we talk about the voltage as being the electromotive force which is abbreviated as EMF. We talk about the EMF of the battery. That's the ideal. That's ideally what the battery can supply. You're going to love this too. We use an epsilon to represent it, as opposed to epsilon naught, which is a constant. EMF is what we use to represent the ideal battery voltage, what ideally the battery is supplying to the circuit. So as we get into this chapter with resistors, instead of seeing this written as a delta V, which you may still see that, but you may also see it written as an EMF.
That's an old term, if I recall, the electromotive force.
It is, it is.
I mean, electrical engineers used to use it 50 years ago.
Yeah.
They don't use it.
Our book still uses it. Most physics books still talk about it.
Probably just because you might still run into it, so you need to know what it is.
Right. It's a little deceptive in that in and of itself it's not a force like in newtons. It is a voltage. But because of the voltage, you get an electric field, which in turn exerts a force on the charges, which is what makes them move. So EMF, epsilon, whenever you see that without the naught symbol, hopefully, it's going to represent the battery voltage.
And it's still in volts, though, right?
It is still in volts.
We don't have to convert it.
Yeah. So you can still think of this as our delta V total, if you want. It's the voltage supplied by the battery. Now, as soon as this battery is connected, and we have all these resistors, right off the bat, there's current everywhere. Since there are no branches, whatever current flows out of the battery is the same as the current that flows through resistor 1, which is the same as the current that flows through resistor 2 and resistor 3. The current, whatever total current the battery pushes out, is the current that passes through each individual resistor. Which that was similar to capacitors. Capacitors have the same amount of charge that accumulated on their plates. Resistors have the same amount of charge per time flowing through them. So in series. Now, conservation of energy, whatever the battery puts in, the elements in the circuit have to take out. So each of these will have a voltage drop. The voltage drop now, though, for resistors, the voltage drop depends upon the current flowing through it and the resistor value. So the EMF of the battery is equal to delta V1 plus delta V2 plus delta V3. Similarly to capacitors, these equations are valid for any one resistor alone or for the circuit as a whole. So the total EMF is the total current times the equivalent resistance that those three would be equivalent to if they were just one resistor. Delta V1 is the current through resistor 1 times its resistance. Similarly, delta V2 is I2R2. Delta V3 is I3R3. But in series, all these currents are the same. when we have resistors in series, the equivalent resistance, to treat them as if they were one single resistor, we simply add them together. Having multiple in series is equivalent to having one that is just a lot longer. Increased length would correspond to a bigger resistance. So our equivalent is simply the sum of all of them, so we get an overall bigger resistance than we would have with any of those individual 3 ones alone. It's backwards from capacitors. Capacitors in series was that 1/over relationship. Resistors in series is straight across. So similar to capacitors as well, we can connect resistors in parallel. The voltage has to be the same for any elements in parallel. To find equivalent resistance, it will be the 1/over relationship. So we can have a group of resistors and have to combine them in series and parallel, like we did with capacitors. Shrink it down, find out how much current this time flows through it, work our way back and find current and voltage for each individual element. Yesterday we looked at resistors in series. As a reminder, remember resistance itself depends upon resistivity of the material, so that's something unique to the material. How long the resistor is and its cross-sectional area. So the resistance of your resistor is completely dependent upon how it's made. By the way, I don't remember if I told you or not, the units of resistance are ohms, and we use a capital omega to represent it. The potential difference across a resistor depends upon the current flowing through the resistor and its resistance. As long as there's current flowing, then there will be a voltage drop. If there's no current flowing through it, it will not have a voltage drop. And similarly, we talked with power. So resistors don't store energy, they convert energy from electrical to some other form. Power can be written in terms of any two of these three, voltage, current, and resistance. One of the 3 ways to write it is I squared R. You can use the equation above it to write it in terms of any of the other 2 as well, if you would like.
A is area?
A is cross-sectional area. So if you were to take the wire and cut through it and look at just the little circle it made, it's the cross-sectional area of that circle. So in series, once you have a complete loop, current will flow, and we're using the definition from long, long ago that current is the flow of positive charges. So current will flow from the positive end of the battery all the way around back to the negative end of the battery. Please keep in mind that current is flowing everywhere in the circuit at the same time. Current does not get used up. So as we look at our resistors, current doesn't get used up by the resistor. Current just keeps going. The charges just keep moving through. If you want to think of something being used up, you can think of voltage. So the first resistor will take a portion of this total voltage. The second resistor will have another portion. Third resistor has the rest. So conservation of energy, whatever the battery puts in, remember E, this epsilon, the EMF represents the battery voltage. Whatever the battery puts in is shared amongst the resistors. Each of them have to have a voltage drop because each of them has current flowing through it. So the total current that flows depends upon the battery voltage and the total resistance of the circuit. So this equation for voltage is equal to IR also works for each individual resistor alone, but it also works for the circuit as a whole. So the battery voltage is equal to the current, total current that flows, times the equivalent resistance of the circuit. Equivalent resistance in a series circuit for resistors is simply the sum of the individual resistors. That's backwards from capacitors. So you just simply add them together. Each of them have to have the same current. The total current that's flowing from the battery flows through each of them. So when resistors are connected in series, they have to have the same current that flows through them. Now, resistors can also be connected in parallel. And just like for capacitors, parallel means there's a branch. The battery pumps out a certain amount of current, but when it reaches this branch right here, some of it will have to come through the middle branch. The rest of it will continue onwards up through the top branch. But charge, even in the form of current, charge must be conserved. So for parallel, we have the total current is equal to the sum of I1 plus I2. The charge can't magically disappear, and we can't spontaneously gain more charge. Whatever charge is moving has to keep moving. Voltage. If we look at the loop, whatever the battery puts in, if I go through this middle branch, the only element I pass is resistor 2. So whatever the battery puts in, resistor 2 takes out.
So on the current, the
IT is the total current that the battery forces to flow.
that's the electrons are moving faster up until they get to where it breaks out.
It's not that they're moving faster, you just have more electrons in this branch moving than in this or this. So whatever total number of electrons are moving per second in this branch, they split up. So only some of that total is moving this way and some of this total is moving that way. So it's not that they're moving faster, it's just that there's more of them moving. Okay. So voltage-wise, battery puts in whatever the EMF is, this resistor has to take it out. So delta V2 is the same as the EMF. But if I follow the big loop, again the battery puts in the EMF, the voltage of the battery, the only element I come to is that resistor 1. So the resistor 1 has to take out all the voltage as well. So it will also have the same voltage as the battery. This is the same relationship we had for capacitors.
Does that also come from the fact that it's all one conductor and they all have to have the same?
Yeah, the potential, assuming there's no resistance in the wires, or very little resistance, all of this portion before it passes through the resistor, all of this portion has to have the same potential. Yes. And then likewise on this side. And so you lose the same amount, you have the same drop across either one. Now to treat this pair of resistors as an equivalent, to find the equivalent resistance that they make up, I'm going to use our current equation and the fact that delta V is equal to IR. I total is going to be the EMF of the battery over the equivalent resistance using this relationship. I1 is going to be delta V1 over R1. I2 is going to be delta V2 over R2. But all these voltages are the same. So equivalent resistance in parallel is a 1/over relationship. So basically our equivalent equations are just backwards from capacitors. From capacitors in series we had the 1/over relationship. capacitors in parallel, they added straight up. It's backwards. Resistors in series, we have this, just add them straight up. Resistors in parallel, 1 over. The nice thing is the same general rules apply. Anything in parallel has to have the same voltage across it. Even if they weren't both resistors or both capacitors. Even if one was a capacitor and one was a resistor, they'd have to have the same voltage drop across it. Okay? And that's just because of the conservation of energy. Anything in series has to have the same current flowing through it. In terms of capacitors, we talked about the charge that accumulated on the plates.